Welcome to Mechanics 1. Today's learning outcome is analyzing single component systems. Analyzing single component systems. The 5-step approach is think about the problem, try to understand the problem, describe the problem mathematically, solve the equilibrium equations, and learn from the solution. Today's problem. Determine the moment of each of the three forces about point A. Let's think about the problem and try to understand what's going on. We can observe that there's three forces that are acting on our body. You can see that there's force 1, force 2, and force 3 down here. And we can observe that we're given an angle for force 1 and 2, and we're given a 3, 4, 5 triangle for force 3. So let's draw a free body diagram. It's always a good idea to draw a free body diagram when it comes to problems like this. The steps for how to draw a free body diagram are outlined below. Draw a rough sketch of the structure, identify the reaction forces, identify the applied forces, and note the measurements. As you can see, the free body diagram is provided on the right, and it highlights all the important information that we need to have when solving this problem. Describe the problem mathematically and solve the equilibrium equations. I think for this problem, it's actually really easy to understand it if we break it up into systems. So we can break it up into systems, one system for each of our force. We have our 250 Newton force, our 300 Newton force, and our 500 Newton force. And we can break it up to solve for each of these systems. So let's look at our first system, system 1. We can observe that we have our 250 Newton force described from the angle given. And the easiest way to solve for the moment is to break it up into components, our vertical and horizontal. We can see that we have two components for this 250 Newton force. We have our horizontal and vertical components. We can see that the horizontal section goes through A. And so we really only have a vertical component we need to take account of when taking the moment with respect to point A. And that's our system 1. We can find a horizontal and vertical component of the force as shown. Sine 30 provides us with the horizontal component, and cos 30 gives us the adjacent component, which in this case is our vertical. So with that being said, we now can solve for the moment at A, and you can see that this is causing clockwise, so we'll have to write it down as a negative. We can see that the distance is 2 meters times our vertical component of 216.5 newtons. Transferring clockwise, we're going to write that as counterclockwise, so it would be negative. Let's look at system 2. We can see that system 2 is our 300 Newton force, and it's given to us 60 degrees off the horizontal. That means that our horizontal component is cos 60 times 300, which gives us our 150 Newton force along the horizontal. And the vertical component would be sine 60, which is 259.81 newtons. Once again, we can see that our horizontal force goes through the line of action to point A. So the moment caused by the horizontal force would be negligible, as it's going through the same line of action as point A. And so only taking account of our vertical component, which is causing the moment, at point A of 259.81 times 5, once again in the clockwise direction. So we note that as negative counterclockwise. That gives us a total distance of 5 meters away, resulting in a 5 times 259.81 Newton, giving us a negative 1,299.05 Newton meters force counterclockwise. Once again noted in the negative direction, since the force here is causing a clockwise rotation, and we noted it as counterclockwise. System 3. System 3 was slightly different than our other two systems, as instead of an angle, we're given a ratio triangle of 3, 4, 5. You can feel free to break that down into angles, but it's not necessary, and you can solve for the system just as is. To find the horizontal component of our force, you could consider a point theta and take the opposite over hypotenuse, which in this case you can use the triangle ratios as 3 over 5 times 500, giving us a 300 Newton force along the horizontal, and adjacent over hypotenuse, which is in this case 4 over 5 times 500, giving us a 400 Newton vertical force downwards. In this case, both of these have their own line of actions that don't cross point A. And so when writing the moment equation, at point A we'll have to consider both. Downwards is 5 meters away in the clockwise direction, giving us negative 400 times 5. And our 300 Newton force is causing a counterclockwise rotation, which is positive, which is 300 times 4, giving us a resultant of negative 800 Newton meters counterclockwise. And that's it. We managed to find all the forces that we needed. You can see that You could take your negative counterclockwise moment and write it as a positive clockwise moment as your last step if you want your answers to be positive.